Hello, my name is Camille, and today I'm going to be explaining the protein acetylcholinesterase and the effects of a specific mutation via my 3D model I made. So, acetylcholinesterase, or ACHE, is an enzyme found in neuromuscular junctions and synapses in the nervous system. Its job is to break down acetylcholine, a neurotransmitter that sends signals between nerve cells and muscles. By removing acetylcholine from the synapse, ACHE stops the signal, allowing muscles to relax. Without it, our muscles would stay consistently stimulated. And I found this on source 1, 3, and 4. So I'm going to give a visual representation. Imagine your nerve cells are sending messages like emails. The acetylcholine is the send button. Without the message, once the message is sent, like telling your muscles to contract, you'll need to delete that message quickly so your muscles don't stay tense forever. That is where acetylcholinesterase comes in. It clears the message or breaks down acetylcholine into acetate and choline, so the signal ends and your muscles can relax. Without acetylcholinesterase, acetylcholine would hang around and keep firing the signal, causing continuous muscle contraction. In extreme cases, this is actually what happens when someone is exposed to nerve agents. It blocks the enzyme and causes dangerous overstimulation of muscles, including the heart and lungs. And I found this on source 1 and 4. The mutation I studied is called Y337A, which means the amino acid tyrosine at position 337 is replaced with alanine. Tyrosine has a large polar aromatic side chain that helps bind acetylcholine in the enzyme's active site gorge. Alanine, on the other hand, is a tiny nonpolar side chain that can't make those same interactions. At the 337th amino acid sits at a crucial part of the enzyme known as the active site gorge, a deep pocket that grabs onto acetylcholine in the enzyme so the enzyme can break it apart. Tyrosine is a large, bulky, aromatic ring with hydroxyl group, which helps stabilize acetylcholine in the active site through interactions like stacking and hydrogen bonding. But when you replace tyrosine with alanine, which has just a tiny methyl group, those interactions are lost. This change significantly reduces how well the enzyme can bind to acetylcholine, meaning it becomes less efficient in breaking it down. And I found that information in source 6. This mutation reduces the activity of the enzyme by weakening its ability to hold onto acetylcholine. As a result, the neurotransmitter isn't broken down effectively. I found this on source 2 and 6. Now I will show you the model I made representing acetylcholinesterase. I used pipe cleaners to form the protein's overall shape with loops and spirals to show alpha helixes, which you can see the spirals up here and down here. Just a note, this color change and this color change down here is insignificant. I just ran out of pipe cleaners. This is meant to be all one color, and this is meant to be all one color. But the rest of them are to distinguish different regions. So, like I said, I use pipe cleaners to form the protein's overall shape with loops and spirals to show alpha helixes and other folded regions. This area here is the active site gorge and narrow pocket where the acetylcholine binds. And I labeled Y337 to show using a large purple clay bead, and the catalytic triad nearby helps carry out the hydrolysis reaction. Then I made a swappable piece down here. An orange bead represents the mutated version, alanine A337, which it is smaller than the Y337 mutation up here. This is smaller than that. And how it no longer reaches far enough to the gorge to help stabilize. So that, yeah. You can also see down here the entrance to the gorge. So to wrap it up, acetylcholinesterase is crucial for proper nerve function. The Y33A mutation helps make the enzyme less active, which can lead to excess acetylcholine and potential problems like muscle overstimulation. Thank you for watching.